Good morning. I'm Eric Reese, Senior Vice President of the Memory and Storage Strategy Division at KIOXIA America. It's our great pleasure to join SNIA once again for our third year participating in the Storage Developers Conference. Today we'll be talking to you about software-defined flash, an upcoming open source initiative to deploy and maximize the value of flash through a software API for all of you in the storage developer community. Let me give you a little introduction to our company, KIOXIA. I had the pleasure of announcing our new name when I first presented here several years ago. Hopefully you're now familiar with the name KIOXIA and our mission, which is to uplift the world with memory. At that time, I stated that the cloud is application driven, in other words, software defined. I still stand by that statement. Today, I want to talk about the opportunity for flash and not the problem, as I previously stated it. Because of scale, hyperscalers must maximize the value of their flash, even every bit. At scale, a small bit wasted multiplies exponentially. Thus, the opportunity I was talking about, to enable flash for software control. Cloud and data infrastructure is software-defined. That goes from networking to software-defined storage. But what about the storage itself? It's about time to apply the same logic to flash with SCF technology. After all, flash is digital. To show our commitment to software-enabled flash technology, last year we released the API and related documentation. The API is OSS or Open Software License. It's GitHub hosted and fully documented. As the SCF API enables the host application to control drive behavior through the SCF host library. The host now has control of data placement, isolation, queuing modes, and the amount of latency needed. As a continued commitment to bring SCF technology to market, we will soon be releasing a software development kit for SCF. And this will be timed with the availability of SCF drive samples. For software-enabled flash adopters, the SDK will speed development and deployment, as well as enabling faster time to market. For those who didn't attend this track in previous years, I'll give a quick overview of what SCF technology is. And after I do this, our chief architect, Rory Bolt, will give more detail on the software development kit and the exciting features we have. Software-enabled flash is a media-based, host-managed hardware approach to storage. Software-enabled flash redefines host interactions with flash, enabling applications to maximize performance and provide otherwise impossible functionality. To put it simply, SCF gives you the ability to extract the maximum value from your solid-state storage. Software-enabled flash is software-defined storage built for the cloud and storage vendors. It's composed of a purpose-built controller and a software stack and API that is open source. The SCF API and architecture are designed with hyperscaler input. SCF technology provides 4 major capabilities: workload isolation, latency control, flash migration, and flash maintenance. I'll talk about each of these. Software-enabled flash helps resolve workload isolation issues such as the noisy neighbor problem. This is where a chatty process can hurt the responsiveness of others on the same server or storage. SCF can isolate and segregate data at the die and superblock level. We call these QoS, or quality of service domains. SCF can control I/O latency at scale. One size does not fit all for workload latencies. Some demand a quick response and can tolerate a few outliers. Other workloads require an optimal average latency that can't tolerate outliers. SCF technology has some queuing knobs that give you better control over latency outcomes. These knobs include priority queuing, round robin, and a configurable die time weighted fair queuing. Flash generational migration can be a challenging process. From the beginning, we designed SCF technology to ease migration from TLC to QLC and beyond. This is vendor independent because of the API. SCF technology provides a higher level of abstraction and hardware offload. This works to minimize programmer effort, host CPU cycles, and PCIe bandwidth. Proper management of the flash media is fundamental to TCO. Software-enabled flash technology gives the host control over the timing of critical media management processes such as garbage collection, wear leveling, and the others that are listed here. Software-enabled flash is really software-defined flash done right. Now, let me turn it over to Rory.
I'm Rory Bolt. I'm the principal architect of the software-enabled flash storage development kit, as well as the software-enabled flash storage software. I'm going to be showing you some examples of what software-enabled flash can do in practice, as well as going over the software development kit itself and how it can make your life as a storage developer better. First is a demonstration that was taken from an FPGA prototype. This started off by defining two quality of service domains with equal die time weighting, and we have a control that allowed the user to manage the weight between the QoS domains in real time and observe the latency response from the system. This is a demonstration that shows how you can define die time allocations for individual applications and then manually override those defaults in response to critical needs for your environment. So once again, software-enabled flash has demonstrated that it can allow you to control the latency outcomes in your environment. The next thing that we can demonstrate is that a single pool of software-enabled flash devices can be deployed and configured in real time to service different applications and even different protocol needs within your environment. Furthermore, these software-enabled flash units can be adapted in the future to new applications and new protocols that may not even exist yet. Once again, the ability to maintain a single inventory pool that can be deployed to different applications and different workloads and provisioned as needed brings great TCO benefits to your environment. Now I'll begin talking about the software development kit itself. The software development kit has four main components: the reference flash translation layer, or FTL, the command line interface, the reference virtual drivers, and a performance testing tool. The first part of the SDK that we'll be talking about is the reference flash translation layer. This is responsible for mapping logical addresses into physical locations within the Ceph unit itself, as well as controlling all maintenance functions within the Ceph unit. Typically, applications interact with storage by going through the operating system. In this example, we've shown what it takes for a Linux application to submit an asynchronous I/O request to the system. First, it defines an asynchronous I/O control block, initializes it, and then submits a read operation in this case. So the application is interfacing with the operating system. The operating system is then interfacing with the device, which traditionally has had its own internal flash translation layer. With software-enabled flash, the picture changes slightly, but the concept overall is the same. Applications now talk with the reference software development kit FTL directly, and that in turn talks with the Ceph unit. Programmatically, this looks very, very similar. You define a context for the operation and initialize it, and then you submit the operation to the Ceph device. The reference FTL makes it easy to convert existing applications. It's a simple matter for normal I/O, read and write conversion. And the reference FTL is provided in full source code and highly modularized with separate modules for logical to physical address translation, superblock management, garbage collection, metadata persistence, as well as instrumentation for both telemetry and debuggability. You can use the reference FTL as is, or extract pieces and design them into your own custom FTLs. As Eric's mentioned, KIOXIA was actually the inventor of flash memory, and we're leveraging our years of experience delivering both flash memory and solid-state disks to deliver a world-class reference FTL. It's fully lockless in its implementation, it's fully multi-threaded, and it takes advantage of all the software-enabled flash offload capabilities built into software-enabled flash. Using the reference FTL, you can experiment with all the different latency controls within software-enabled flash. So you'll have control over die time waiting, you'll have control over maintenance tasks such as garbage collection, control over provisioning for your storage, as well as control over data placement for both isolation, physical isolation of workloads and data, as well as write amplification. The benefits of the reference FTL are that it enables a fast transition to software-enabled flash. It's highly configurable to meet specific application needs, and overall, the goal is to reduce time to market with new and innovative storage solutions. You can use the FTL as delivered, or once again, you can customize the FTL using the source code that's supplied to create new application-specific flash translation layers for your own storage needs. The next component of the SDK that we'll be talking about is the command line interface. The command line interface actually supports every single function of the software-enabled flash API. This particular example is using the command line interface to create a quality of service domain. We're going to skip over all the nitty-gritty details here, but I'd like you to focus on the lines, starting with number of flash media queues being 4. This is defining how many different queues can be used for scheduling operations in this QoS domain, and then a block of weights. And these are die time weighting allocations for different types of operations that can happen within this quality of service domain. And then finally, we have the assignments of the different types of flash operations to individual submission queues within the quality of service domain. This is a highly configurable system that allows you very tight control over die time and queuing allocations within the unit itself. The benefits of the Ceph CLI are that it's easily scriptable and integrated into any sort of automated deployment system or provisioning system. It supports, once again, all of the functions of the API itself, and it even includes a Python interpreter so that you can actually supply Python programs to the CLI to execute software-enabled flash directives. Using the ability to define QoS domains allows you a way to specify dynamically the provisioning of storage and the characteristics of that storage on a per application basis, a per virtual machine basis, or a per container basis. Next portion of the software development kit that I'm going to be giving an overview on is the reference virtual drivers. The reference virtual drivers are QEMU device drivers that support both standard block mode interface as well as the ZNS protocol. These virtualized devices make the translation from either standard block semantics or the ZNS protocol to software-enabled flash and allows you to run programs in virtual machines unaltered that can talk to either standard block storage or ZNS storage. No code changes required whatsoever to evaluate software-enabled flash with existing applications. Since these are virtualized devices that plug into the hypervisor itself, they're transparent in operation to the guest operating systems. The virtual machines see only regular block devices or ZNS devices. They do not know that it's software-enabled flash underneath. Once again, as with everything in the software development kit, all source code is provided so that you can adapt this, support other protocols if you like. Finally, when coupled with the Ceph command line interface, you can demonstrate and evaluate the benefits of quality of service configurations and multi-tenant isolation support within your environment. So you can define different quality of service domains that have different bandwidth allocations, different weighting for the scheduler. You can assign them to individual virtualized instances of the block driver or ZNS driver. And so you can have competing workloads running isolated from each other in different virtual guests without writing any code and observe the performance of the software-enabled flash system. What are these benefits? Well, once again, you can customize over provisioning on a per virtual machine instance. You can even do thin provisioning, that's supported. So you can maximize the utilization of your flash and migrate jobs as required when you're running out of physical capacity. It goes without saying, we can instantiate multiple VM instances on a single Ceph device. Those individual instances can be running the same protocol or different protocols. It doesn't matter to us. Also, this is all fully VIRTIO compliant. And in conjunction with the CLI, it allows you to preserve data and performance isolation between tenants in your multi-tenant environments. The last portion of the SDK that I'll be talking about is, in fact, the performance test tool. Since you're here at Storage Developer Conference, I'd be very surprised if you hadn't been exposed to FIO. It's an industry standard tool used by many corporations to characterize and benchmark storage solutions. What we've done for the SDK is we've created a software-enabled flash-specific plugin engine to FIO. This allows you, once again, in conjunction with the command line interface, to define differing QoS domains with different performance characteristics, and then submit standard FIO workloads against them to observe the capabilities and performance of software-enabled flash. So you can test your latency controls, you can test your isolation controls, you can prototype your system performance. If you know how to write FIO scripts that will model your application's performance, you can observe how software-enabled flash will handle your workloads. And you'll get tired of me saying this, but once again, all source code is included in the SDK. Now I'm going to be turning the presentation back to Eric so that he can summarize and point you to where you can find more information on software-enabled flash.
Great job as always. So what does the combination of software-enabled flash, the SDF API, and the SDF software development kit mean at the end of the day? The net are real TCO benefits for storage developers. We have a list of the things we talked about today, such as accelerated development process. The abstracted nature of the API lets you focus on what's important to you in your application development. Also, faster application time to market and a full exposure of the full digital nature of Flash, allowing you to be more creative with how you want to deploy workloads and storage in your environment. SCF is built on host-controlled, purpose-built hardware driven by an open-source software-enabled Flash API. The SEF software development kit builds on SEF technology, providing a reference FTL, a virtual IO driver, a scriptable CLI, and a test suite. This SDK will make it faster and easier to evaluate SEF technology and help shorten the time to market for SEF native applications. We understand that multiple hardware sources are needed. Therefore, we're setting up a community-based open source software project with a world-renowned entity. This project will provide independent access and neutral management of the open standard. Because SEF is an open standard, it will be free for use by vendors, co-travelers, and developers. There's no reason for Flash not to be software defined. Therefore, we give you software-enabled Flash. It's been architected and built to maximize the value of Flash while making it easier to use and faster to deploy, thus giving Flash an even better total cost of ownership. So for more information about SEF, please see our microsite, softwareenabledflash.com, for updates on the SDK and its availability, as well as other updates, because we are actively developing and actively bringing this to market. You'll find white papers as well, and all other information. We do have a GitHub for the API before it transitions to the open source project. Thank you all for being here and making time to listen to this presentation. I trust and hope that you found the time useful in learning more about this exciting technology that we're bringing to market that really will unlock a lot of the potential of Flash, which still has a lot of potential. I also want to give a thanks to the Software Developers Conference for allowing us to use their forum and sharing this message. And again, a big thank you to all of you.